Hello, I'm going to talk a little bit more about the force-length relationship, specifically the active force. Students tend to confuse this a lot. With the active force, that's the actin interacting with the myosin. And that active force, you've got force per length, and that active force is typically shown as a bell-shaped curve. Intuitively, what you can see very clearly from this diagram is that at low or short lengths, you have low force. At long lengths, you also have very little force generated. And at an optimal length, you've got optimal force being generated. This is the active force. So how does this happen? Students have a lot of problems with this. As I mentioned, you've got the actin interacting with the myosin. So you have actin here, you've got myosin here. They interact with each other and pull to generate a force. So this actin is pulled upon by the myosin, generating force. That force that you measure here, importantly, depends on how many of the myosin head groups interact with the actin. In skeletal muscle, typically when you have stimulation of the muscle, all of the myosin will interact with the actin. But there's always an exception, and this exception is when you stretch the muscle to different lengths. So here is the sarcomere. You have your thin filaments, or your actin, shown here. And you have your myosin, shown here, with little head groups. And let's just do 5. So you've got head groups, and they're on either side. So I'll just draw them on either side here. So this is your myosin. The myosin will interact with the actin, generating a force. The myosin on this side will pull the actin here. Myosin on that side will pull the actin in that direction, and you'll get a shortening of your sarcomere with the myosin in the middle. This is not drawn exactly to scale. So you've got your myosin here and your actin, and the sarcomere shortens. That's how the force is generated. And this is what happens typically in your skeletal muscle. What's happening in this experiment, what we're doing is we're actually measuring the amount of force at different lengths of this sarcomere. So we're not allowing the sarcomere to shorten, we're measuring the force that the sarcomere or the muscle element can generate at different lengths. Let me just clear the screen a little bit. Now that I've cleared the screen, I can show you that diagrammatically. It's very easy to show what happens when the muscle gets longer and longer and longer. What happens is you're stretching out the sarcomere. So diagrammatically, at optimal lengths, you'll get all of the myosin head groups interacting. Okay, let's just do 1, 2, 3, 4, 5. So all of these are interacting. So we'll just look at this top part here, and this is the myosin. And this in this color is the actin. So you have 100% interaction. 100% interaction. That's very clear. This is the optimal length. If I stretch it a little bit more, what we will have, and I'll just draw the myosin in here for a reference frame. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If we stretch it a little bit, and the actin does not overlap efficiently with the myosin, we'll get a reduction in force because less of these myosin head groups can interact. So if this is 100%, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 interacting. Here we've got 1, 2, 3, 4, 5, 6. 6 of the total amount can interact. Therefore, we're getting, we'll be at this longer length, so the length is longer, we will be getting 60% interaction. If we stretch this muscle so much that there is absolutely no overlap of the actin and myosin, then there'll be no force generated, which is indicated here, 0 force generated. And this is what happens when you stretch it very long. Okay? So that's how you can explain from this part of the curve down to here. As the muscle gets stretched to longer lengths, you get a lot less myosin-actin interaction. I've cleared the screen a little bit, and now I'm going to talk about what happens on this portion of the graph. This portion of the graph, you get shortening of the sarcomere. It's a little bit more complicated than elongating of the sarcomere, because what you have here at shortening, so this is optimal. When you get shortening, you get some of the actin overlapping with each other. So you don't get optimal myosin interaction with actin. So some of this actin will interact with that myosin. Okay, and as I mentioned before, this will be pulling this way, that will be pulling this way. So when it gets shorter, you get complicated interactions. This actin here will interfere with that myosin binding. You get pulling in all different directions. For example, if this binds to that, you'll get movement that way, instead of this binding to this one, and you get movement that way. And so you get interference of the different actin with the myosin. So the myosin will not have optimal binding, and force will decrease. So that will result in a decreased force. And I'll say decreased force here. If you shorten the muscle to such an extreme length, what you will happen, in addition to the overlap, is this myosin will bump into the ends, into the Z discs of the sarcomere. So you cannot get any further shortening. So that's what happens when you have shortened to very, very long, That's what happens when you shorten to extremely short lengths. You will actually get 0 force. So the active force shown in this bell-shaped curve is due to myosin interacting with actin and generating force. You have an optimal amount of overlap of myosin head groups with actin. If you stretch the muscle too much, you'll actually reduce that interaction, and you'll reduce that force. If you compress the muscle or shorten the muscle too much, you get actin interference. So you get reduced force, and if you shorten it too much, the muscle just can't shorten anymore, and you'll get 0 force. Diagrammatically, this interference can be shown when you slice the muscle in cross-section and look at the myosin-actin interaction. So here you have myosin, thick filament, surrounded by And I'm just doing that hexagon so that I can draw the actin. So here's the actin, and in the middle is the myosin. If you shorten this sarcomere too much, what you start to see is that other actin start to compete for this myosin cross-bridge interaction. So these are the myosin cross-bridges. So you get competition of the actin as shown in here. And we obviously can't demonstrate that there, but that illustrates how the actin can interfere with the myosin action when you shorten the sarcomere too much and you reduce the force. So in summary, we've demonstrated the active force, and we've shown how this active force is altered by the length of the sarcomere.